Hey, what's up, everyone? Welcome back to another explainer. Today, we're going to tackle a really classic, really cool physics puzzle: how to figure out the electric field from a charged arc of wire. Now, I know that sounds a bit heavy, but trust me, we're going to break this whole thing down piece by piece. So here's the big question, the real challenge of this whole thing. How on earth do you calculate the force from an infinite number of points all at once? See, the charge isn't just one neat little dot. It's smeared all along this curved wire. That means you've got countless tiny points, each one generating its own little electric field. So how do you add up, well, infinity? That, my friends, is exactly why calculus was invented. All right, let's set the stage. Here's the challenge. Imagine you've got this arc of wire. For our problem, it spans a total of 120 degrees, and it has a uniform charge all the way along it. Our mission, should we choose to accept it, is to figure out the total electric field right at the very center of that curve, a spot we'll call point P. So how do we tackle this? The strategy is actually pretty genius. Instead of getting overwhelmed by the whole arc, we're going to do what physicists do best: break it down. We're going to zoom way in and look at just one teeny tiny piece of the arc. I'm talking about an infinitesimally small slice. It's so small we can basically pretend it's a single point charge. And we'll call this little bit of charge dq.
And this is a really key point. Thanks to Coulomb's law, we know that each of these tiny little dq pieces creates its own tiny electric field, which we'll call dE. And because our point P is right at the center of the circle that this arc is part of, that little field vector, dE, is always going to point straight from that charge element, right towards the center, P.
Okay, and now, my friends, comes the secret weapon, the clever trick, the aha moment. Before we even think about writing down a single equation, we're going to use the most powerful and, honestly, the most elegant tool in a physicist's toolkit to make our lives way easier. We're going to use symmetry. Just think about it for a second. Our arc is perfectly symmetrical across the horizontal axis, right? It's a mirror image of itself. So what does that mean? It means for every tiny little piece of charge, dq, you pick on the top half of the arc, there's an identical twin, a perfect counterpart, on the bottom half.
So what's the big deal? Well, let's look at the electric fields from these two twin charges. The top charge creates a field with a vertical part pointing down. The bottom charge creates a field with a vertical part pointing up. Since they're perfect mirror images, these vertical components are exactly equal and opposite. So, poof, they completely cancel each other out. They're gone. But what about the horizontal parts? Both of them are pointing in the exact same direction, to the left. So they don't cancel. They add up. They reinforce each other.
Do you see how huge this is? Without doing a single bit of math, just by thinking about the shape of the problem, we've figured out that the total electric field has to be purely horizontal. The entire vertical component is just zero. We've just sliced our problem in half. This is exactly why I always say symmetry is the most elegant shortcut in physics. All right, so symmetry did the heavy lifting and cleared the path for us. Now we get to build the actual mathematical tool we need to calculate what's left over, that total horizontal field. To do that, we need to introduce a super important concept: linear charge density. We use the Greek letter lambda for it. Don't let the name scare you. All it means is how much charge is packed into each little bit of length. Think of it like jam on toast. It's the amount of jam per inch of bread. Lambda connects the charge, dq, to the length of that little piece of wire, ds. It's our recipe for charge. Okay, so let's walk through the steps here. Step 1, we write down the formula for the tiny electric field, dE, from our tiny piece of charge. Simple enough. Step 2, we know we only care about the horizontal part, right? So we grab just that piece of it by multiplying by the cosine of the angle. That's our horizontal component, DEX. And finally, step 3, we just clean things up a bit, substitute in our definitions, and we get this nice, clean formula that's ready to go. This right here, this is the fundamental building block we need.
We've got our building block. Our tool is ready. Now it's time for the grand finale. We're going to use the power of calculus, specifically integration, to do what we set out to do from the very beginning:
Add up all those tiny horizontal pieces from every single point along the arc. So what does integrating actually mean here? It's just a fancy word for summing up. We're telling the math to start at one end of the arc, at negative 60 degrees, and add up the horizontal field from every single piece as we sweep all the way to the other end, at positive 60 degrees. The integral is just the tool that does all that tedious adding for us. And here's where the math gets really elegant. The integral of cosine is just sine, a nice, simple function we all know. And when we plug in our limits, from negative theta to positive theta, we get to use this super handy trig identity. Sine of negative theta is the same as negative sine of theta. So when you have sine theta minus a negative sine of theta, they add up. The whole messy integral just simplifies down to 2 times sine of theta. How cool is that? And now we're on the home stretch. We just plug in the numbers. We know our semi-angle, theta, is 60 degrees. We know the result of our integral is 2 times the sine of that angle. The sine of 60 degrees is the square root of 3 over 2. You plug that in, the 2's cancel out, and boom, we have our final answer. That is the magnitude of the electric field at point P. Okay, we have an answer. But can we trust it? A great way to test any new physics formula is to push it to the limits. See what it says about a situation where we already know the answer. Let's give it a final test, a reality check. So I'm going to throw this out to you. What if our arc wasn't an arc anymore? What if it was a complete closed circle? Just use your intuition. Think about the symmetry of a perfect ring of charge. What do you think the electric field should be right in the dead center? Okay, let's see if our shiny new formula agrees with our intuition. For a full circle, the arc goes all the way around. That means our semi-angle, theta, is now 180 degrees. So what's the sine of 180 degrees? You got it. It's 0.
And if that sine term is 0, the entire electric field becomes 0. Exactly what our intuition told us should happen. It just makes sense, right? For a perfect ring, every little bit of charge has a buddy on the exact opposite side, and their fields cancel out perfectly at the center. So our formula didn't just solve the arc problem, it passed the circle test with flying colors. And that, my friends, is the power, the beauty, and the incredible consistency of physics. Thanks for watching, and I'll see you on the next one.